Buenos días a todos. Welcome everybody. Today's seminar will be given by Dr. Didier Grandjean. Didier is a senior researcher working in the physical chemistry and material science at the quantum solid state physics section of the Department of Physics and Astronomy at the KU Leuven in Belgium. Didier is specialized in the characterization of the structural and electronic properties of functional nanomaterials using principally synchrotron-based X-ray absorption fine structure spectroscopy technique. Okay. His research topics range from studies of oligomeric luminescent clusters confined in organic and inorganic scaffold over in operando investigation of electrocatalysts based on size-selected multimetallic clusters, size and carbon substrates under reaction conditions. So, Didier, thank you very much for accepting the invitation, and the floor is yours now.
Yeah, thank you, Eduardo, for the introduction and for the invitation. So I'm very happy to be in Mexico. I would have preferred to be physically there, but okay, it's better than nothing. So now I want to present something about X-ray absorption, and I thought probably few of you had some real experience with this. I've started with some introduction about EXAFS absorption spectroscopy. And for the cluster, you see, I put here already two clusters. Why I call them cluster. This is the cluster, silver cluster that you can find in a zeolite. So you see, this is an oligomeric cluster, 4 atoms, and this is the bigger cluster that is a bit 3 nanometer, is about 800 atoms. So in principle, this big cluster should be called nanoparticles. So I will call them cluster because we use a cluster machine, but people are now referring to them to nanoparticles. Yes. So just to start, I wanted to ask a simple question about EXAFS, just like a short introduction. So here I put the 4 different stages of the treatment of the data. You have the raw data, you normalize, you do EXAFS, and you do Fourier transform. So in more detail, what is EXAFS? It's the modulation of the X-ray absorption coefficient at energy near and above an X-ray absorption edge. So there are 2 regimes that are well known. There is the ZENS, which is very close to the edge here. And then you have the EXAFS, that is the long range, can go like 1000 EV after the edge. And this is called extended X-ray absorption fine structure. So in general, EXAFS characteristics, you get the information such local atomic coordination, chemical oxidation state. The good thing is that it applies to any element and is also specific for each element because each element has its own edge, of course. And it works at low concentration, minimal sample, so it's a good technique. How do we measure it? There are several measurement modes, let's say. The most common one is the transmission. Transmission is just like a typical absorption, the Beer-Lambert law. You have I0, so you're just measuring the absorption during the sample, inside the sample. The absorption, of course, it corresponds to this excitation here. This is the best way to measure, but of course, you need to have the right sample. You need to have a good concentration, otherwise. Then the second method is the fluorescence measurement. So now you're going to use once the electron has been excited by the X-ray, it will come back, and during the comeback, it will emit some fluorescence. And you will measure this fluorescence is exactly similar to transmission. You will get the same EXAFS spectrum. And this is good for diluted sample. It's also good if you cannot go through the sample, if your sample is mounted or something very thick, then you need to measure fluorescence, and then you measure at 45 degrees. And then I will show you, there are other ways to measure EXAFS. I will show you later. So ZENS, in general, is comprised the pre-edge. Sometimes you have the edge here at the edge, and then this is the sort of structure close to the edge. You know the rules of the dipole selection rules. So of course, K edges, it's a transition for S to P and L to 3 edges, P to D. And this is all the elements that can be reached, for instance, at double at the SRF, which is a typical beamline. You see only the very light element cannot be reached here because they are too low in energy. But this can be reached, for instance, at Bessie in Berlin. There are also other synchrotron that are working at lower energies. And you see this is the different transition that you can have. So you go from 1s, and then you have all these bound states, and then you go to the continuum. What information you can obtain? Actually, you can obtain already a lot of information from ZENS. The white line, so the white line is a very huge peak here that's forming just after the edge. It's just depending on the unoccupied states. So it means if you have something very oxidized, then you have a huge white line. If it's not very oxidized, it's very small. Then, as I said, you can have some forbidden transition that becomes allowed because of the change of geometry. For instance, here it is becoming tetrahedral, and suddenly you have a pre-edge appearing. And the main characteristic is the position of the edge that gives you the oxidation state, which is pretty reliable. So it's increasing with the oxidation states, except for silver, unfortunately. And then what you can do with you can already do things with ZENS. You can follow a reaction. For instance, if you just follow the intensity of the white line, then you can already see that this is the crystallization of Alpo. And you see that at one temperature, suddenly there is a change here. And you can also follow this little pre-edge. You see, and everything should work in, of course, in agreement. And you see the change of coordination during the crystallization for octahedral to tetrahedral. So now, after the ZENS, you have the EXAFS. EXAFS is a bit different because now you're outside the bound states, you are in the continuum. And so now you will start to have some interference. You have a wave that is going to travel into your material, is going to meet at the other neighbors. The other neighbors, they will also emit. So it's like a surface of water with some drops of water. You have a lot of waves going, and then you have a pattern of interference, which they can be in phase, out of phase, and this is reflected in the variation as a function of energy. Each energy will give a different pattern, so you just have this variation here. Here, this is the formula of EXAFS. I mean, this is just describing as a function of the wave vector. What is interesting here is all the colored letters. N, so it's based on N, R, and sigma, plus F and delta. So F and delta, there are amplitude and phase shift that are typical of the element. So you see, you can already have some specificity. You know which atom it should be. I mean, it's not 100% specific. And then you have these three parameters: the distance to the neighboring atom, the coordination, and the disorder. So this is what you can obtain from EXAFS. So how to treat the EXAFS? You have to do a sort of a bit complex treatment, because you see this is the typical EXAFS, let's say, absorption you get, and all the information is only here. So it's maybe 10% of your spectra is the information. So you have to extract that. So first you have to smooth a polynomial that corresponds to a bare atom background. So you have to find the right way. It has to go in the middle. So it should have no oscillation because it's one single atom. And then you subtract, and then you obtain that. And then you multiply by k, and you change the instead of energy, you go to the wave vector, or it's just a mathematical treatment. And then Fourier transform that gives you all the frequencies that are inside this wave. And this is the final EXAFS that you will have to fit. Let's say you will have to build a model. The program will help you, but you have to build a model that will exactly reproduce this wave. The problem is that they could have several models that could fit the wave. So now I go to the first part of presentation. This is the work we did with Eduardo on the luminescent zeolites. And of course, we've done a lot of work on this. I mean, this system has been studied for more than 40 years, a lot of controversy, a lot of discussion. It's an example of what things can go wrong in science. And so I want to be a bit more specific. For this study, we went, of course, to ESRF, Grenoble. So I just put the ring here. So this is about 800-meter long circumference. This is a view of inside. So you see it's quite big, and you have all these beam lines. They're all, you see, this is the storage ring. So once you have accelerated the electrons, they go inside the storage ring for a long time, and then they produce X-ray. So to produce X-ray, you need to accelerate electrons. So here in Grenoble, we have two ways to do that. You see, each line is a beam line, and each line corresponds to a device inside the storage ring here. So the electrons are going like this. And so you have two types of instruments. You have insertion device that are like a succession of magnets, so they can really have a very high flux. And now with the new refurbishment, it's very high. It's 10 to the 16 photon per second maximum. And we also have the bending magnets that are used to make the electrons circular, but they also produce quite a good flux of X-ray, a bit low, but it's still very useful. So basically, we will use bending magnets. So this is the beam line we use. It's just a description. This is the Italian beam lines. You see, even in the synchrotron, some countries have bought some beam lines. So this is the typical beam lines. So here is the storage ring. So the beam is coming in like this. So all the lines are a bit equipped like the same way. You have OH is optical H, and you have basically mirrors that for the focusing. And you have the most important is the monochromator, which is double crystal silicon that has to define the exact wavelength, because you know that the light coming from the X-ray is white. So he has all the wavelengths. So you really need to select the exact wavelength with the two crystals. So this is a big machine, and you also have this mirror for the focusing. And this experimental rush is where you do your experiment. Here you have two, but okay, there are different configurations. I just put some photograph of the different instruments to give you an idea of the size. It's pretty huge. So this is in terms of meter of, you see, hundreds of kilo or tons. And this is the monochromator here. You see, this is the round shape. It's working in everything, of course, is working in vacuum. Here it's not connected, but it's working in vacuum. You have, in general, you use silicon monocrystal, single crystals, 111 or 311. It's a double crystal, so you have to meet the diffraction condition to have the right wavelength. And you see the two mirrors here. Okay. So these are the two experimental H's. And you see every time you have a lot of equipments that allow some measurements under different conditions. You can have a high temperature, you can have a control atmosphere, you can use different cells. And what I'm going to show you is another mode of detection of EXAFS, which is ZEOL, X-ray excited optical luminescence. So now we are going from the X-ray, which is about 10 keV, and we should collect the signal in the form of optical luminescence, which is 2 or 3 eV. So of course, it's photon in and out technique, and there is a huge energy loss cascade. So it's, I mean, very difficult to understand. Few people really understand how it works, because going from kilo electron volt to few electron volt. But what is interesting is that normally it should give you something that can probe the local order. So in principle, you can measure also EXAFS with this light, optical light. And here the setup, you see this is the sample here, and you have just a lens that is collecting the emission from the cluster. And so X-ray is here. So here you can measure the transmission with X-ray in before after. But at the same time, you can measure the optical light produced by the sample. So you have lenses, optical, and detector, data acquisition. So you measure both at the same time. And this is the interesting thing. So I'm sure you are aware of this material. These are the LTA exchange with silver. So yeah, it was seen that after this thermal treatment, they became extremely luminescent. They are a bit pale yellow, but they also show a huge green luminescence, and it's also inside. It's not just on the surface; it's the full crystal that's becoming luminescent. And you see here the 2D plot. Emission to so different, mainly one emission and different excitations. So zeolite also probably you structure. These are nanoporous matrices. So these are just tetrahedral of SiO4, LiO4 that are making this very complex structure. We are mostly interested in a sodalite here because but sodalite is a special cage that is let's say constituting the structure of this LTA and phosphosite. So this is the typical LTA. So I put in different color the different cavities. So you see the small connector in blue. They are too small to contain any atom. Then you have the sodalite here. And then you have the super cage in yellow, and then we transfer into atoms here, and then you have the sodalite here. So there are a lot of rings, 8 6-ring and 6 4-rings. And yeah, these LTA, of course, they have a silicon aluminum ratio. The problem is that L3 plus cannot balance Si4 plus, so you need to add each time you put an aluminium, you need to add an extra from cations. So it will be sodium, potassium, and here we're dealing with potassium. And then you can also exchange this potassium by silver. So you can do a lot of changes in the structure. This is not exactly the structure of the zeolite, but is sort of associated with the structure. And then we're going to have a look at the Ag3K9, which is partially exchanged. So there's been, as I said, there's been a lot of work on this system for 40 years. I think it's even started in K11 in the 80s, I think, and 70s even. And this is one of the first measurement of cluster, of silver cluster in zeolite in 78. And they measure some Ag6 cluster with the XRD, which is not bad actually, 12, so it's fully exchanged. And then the cluster has also been observed Ag6 with the stem a bit later. But the problem with this investigation, of course, you don't know whether this system you are now seeing are luminescent. Actually, they might not be luminescent, and you don't know if the system is hydrated, dehydrated. Everything is measured in vacuum very often, and even EXAFS was not very successful because, as you see, you have a lot of different sites, and it's very difficult to find an abnormality. So to try to find another solution to unravel the structure, then we went to this XEOL. We had some tests before, so this is also a very interesting test that's showing that how the beam is controlling the cluster. So it means why it's a bit it's explained a lot of the problems that people run into. Is that, as you see, you can either form the cluster in the beam if they are not formed, or you can also destroy them if they are formed if you irradiate longer. So this is a typical pellet, and you see each line is a irradiation of maybe 10 seconds, and you're forming the green cluster, and in the middle we irradiate for a long time, and then you kill everything. And if you look at the heat treated and the extra activity, they're exactly the same. Also interesting with the XEOL is that we can measure the shape of the pellet after as a function of the optical luminescence. So it gives you how much cluster have been created or destroyed. And you see this is the position of the beam. And you see if you irradiate for some time, you're increasing the luminescence, so you're creating new cluster. And now if it's after a while, 2 hours, if you continue, you're just decreasing, you're just digging into the sample, and then you sort of destroying the cluster. So that's why it's so difficult. First measurement of XEOL XAFS. So this is the AG3 edge, and so you see the XEOL edge is in black, and the transmission. So transmission, they are measured at the same time, and they are not the same. So you see that the two detection modes, they are measuring the same sample, but they don't see the same thing, which is interesting actually. And so the problem also, as I said, the oxidation state is not available, but okay, this is something we can later. Now, what is the EXAFS measure about the XEOL of this AG3 system? So as I said before, this is the EXAFS that we have extracted. This is the fit. You see, in blue is the EXAFS. The fit is the model I have fitted inside my computer, and it should. You see also the fit of the Fourier transform here. And this is the model here. And you see you have like, I would put 4 shells. The first shell is the first peak here, is oxygen, the distance. The second peak is this one, is 3 silver, so 282. And then you have potassium at longer distance here. And then this is the agreement factor. And of course, this is all you get, so you need from this, you need to rebuild the structure. And N2 obviously gives you see, if you have 3 silver, it means it's forming AG4 cluster. And the distance is there. And then on top of this, you have AGO distances. And we find out that this was a water molecule, extra framework water molecule. And then you can sort of try to work out the fraction of the two possibilities, 2 water and 4 water. So we end up with 2 isomers, like 60% of silver cluster surrounded by 2 water and 40% surrounded by 4. And then you have additional silver and probably more potassium around the cluster. So this is what we find from the XEOL. And from this investigation, we know that this structure is the luminescent structure. Now we just compare, we can compare with the transmission data, which is measured exactly at the same time. And as you see, this is XEOL and this is transmission, and they are not alike, different profile. And if you analyze the transmission, so now the transmission, of course, you see everything. You see all the silver, even the one that are not luminescent. And now we need to, so it's a bit similar to before, but now we need to add this shell, which is the silicon aluminum shell. So this corresponds to these atoms that are in the ring of the sodalite around the cluster. So we have the cluster, and then we are surrounding by a lot of silver. And then, of course, it's adding a shell, and it's complicating everything. And then we see with there's quite a good agreement, but we have some distances changes with the XEOL and transmission. Okay, this is something that also been observed in theory. So I think it's, if you have both the XEOL and the transmission, then you can sort of build a model. You see, that's the model I had to build. So normally all the distances you have, they should match. Because if one doesn't match, it means there is something wrong. And this is the final model we obtained. So the sodalite, the Ag4 cluster, tetrahedral cluster in the middle, surrounded by water in the face, and you have this additional silver. So you see it better here. So now from there, once you have a very nice structure as detailed as this, I think it's very interesting to do theoretical optimization to understand exactly how the electronic things work. So we that with Min at the university in Quang. They are Vietnamese. I was a Vietnamese fellow here, and I'm still working with him. And so once he has the exact structure, then it's much easier for him to start building a model. So this is the model he built with the cluster, and then he has to optimize it. So he just optimized it. He has to implement a charge with this natural bonding orbital, and then he finds two isomers, 4 and 2, and this is what they produce in terms of luminescence, the 2 and the 4. And you see, if you compare to the experimental, it's very close. So I think they are very good agreement with the experimental. And then once you have this optimization, you can really calculate the orbitals of the cluster, all the orbitals, and then that's the system we end up with. So it's, I mean, we call it a super atom, which it means it's mimicking an atom. So it's a cluster, several atoms that are resembling their property, electronic property resembling like an atom of helium, for instance. This is 2-electron system. So you have the HOMO is this S spherical orbital, and then you have the p orbital, the LUMO, or the p orbital. So of course p orbital, p, x, y, and z. And then this is the calculation of all the energies. And you see also the singlet, triplet states. We also show that the water molecule was lifting the degeneracy. So you see this is with no water, and then suddenly if you put water, you see the separation of the states. And we concluded that the emission was coming from the lowest energy of the triplet state, and this is here. And this corresponds roughly to the energy of the transition that has been observed, experimentally. So I think this is, I mean, when you can reach this agreement, it's very good, because very often theoretical work is a bit, I would say, out of control. So in conclusion of this part, so I think we were able, because we use this combination of techniques to really unravel the origin of this luminescence. I mean, this was very important to understand where it was coming from. And we saw it was a mixture of doubly charged tetrahedral Ag4 species. And we could even see that the water had a key role on the luminescence, the band gap. And super atom, I think it's a very interesting feature of this cluster. And now we're still working on other systems, so we need to improve the understanding of this. So is it applicable to other cluster? We have to see it. I think we are working on new cluster in also zeolite or similar aluminophosphate, and there are still interesting things to discover, I think. So this is the first part. I want to thank the people that work on this topic. Eduardo, of course, Kong from Vietnam, Eduard, Walter, Tale was my student, Philomena. This is the BIM line scientist, Martin Hoffers. This Pinto is the professor doing the Ph.D., one of Kelsen and Italians. Now I go to the second Ah, no, it doesn't. I cannot stabilize. Okay. So now is the design of methanol catalyst. So we have let's say in our group in physics, people are specialized in making cluster, but they're making physically. So they're making cluster in a gas phase. And now the idea was to try to apply this cluster to as catalyst for methanol. So it could be methanol oxidation for methanol cells, or it could be now also for CO2. You see CO2 transformation into fuels. This is a very hot topic now, and we have this new ETN CACHI. You can have a look at the website. There are 14 students working on this topic. So the idea is to transform CO2 into ethanol, ethylene, or methanol, but by two ways. Either it could be by hydrogenation, thermocatalyst, or by electrocatalyst. So there are two ways, so there are people different in two directions. And you see, these are the cluster we want to use. I don't know why he's doing that this one. So we want to use this cluster that they deposited in the gas phase. I will show you how we make them. No. Oh. So to design, so the idea is to design new catalysts. This is not a very easy topic, because catalysis is very complex and there are so many parameters and very difficult to observe because, of course, everything is happening in situ. So basically, if you want to design a catalyst with cluster or nanoparticle, there are three parameters that you need to consider. Of course, the size, because it's controlling the surface structure, the density of active sites. You need, for instance, you see that the work, all the work that show that at one precise size, then you have a huge activity. Then the nature of the support, because you have the support interaction with SiO2, especially with TiO2. And also what is important when you're doing bimetallic cluster, because that's what we want to do. We want to use bimetallic. So the problem with bimetallic is that you can form, actually it looks from far away, it looks like you have two metals, but you see you can have very different distribution. You can have the Jan slag, you can have alloy, you can have core shell, you can have, this was computed by Ricardo Ferrando, but I guess most of them can exist. So once you have this, you don't know which one is on the surface, so you really need to do a very, very deep analysis, and EXAFS is also a very good technique for this. But of course, especially for biometallic, but EXAFS is not enough. The problem with this investigation, EXAFS is one of the investigation techniques I will show you, but unfortunately, you cannot do everything with EXAFS because EXAFS will not give you the interaction with the molecules, etc. So this is the, let's say, idea of how we can design new catalysts. So we have this machine that are making well-defined bimetallic cluster. We deposit them on, it can be anything. It can be a support silicon wafer. It can be a powder. Some companies is depositing onto a powder. So you can make like a normal catalyst. Then you have TM grids. Then the idea is to do operando characterization. So it means during the reaction. That's why the EXAFS is there. And we can even have electrochemical cells. So it can be in gas. It can be also in the electrolyte, you see, in electrochemistry. And then we also doing now TM in situ with the group in University of Antwerp. So they have received their first cell. It's very preliminary. And then we do the catalytic test. So as I say, if it's powder, it can be in a typical reactor, gas flow reactor, or we also using TPD, the temperature program desorption. We have a setup here. I will show you later. And then of course we have the DFT modeling in the middle that should help us to maybe to predict or to understand what we've done. But this is of course very ambitious. So how do we make our cluster? So basically, there are two machines here. One is the magnetron. So it's cluster beam deposition. So you see everything is in vacuum, and you're ablating a target. Target is a bulk metal piece. So if you want to produce cluster of silver, you are ablating a silver metal ingot. So you see, you have this the sputtering chamber. You have a gas. Argon is going there, so you have the magnet here. You have a plasma. You're making the cluster. Then the cluster, they are inside the gas. It's like a beam. They go there. You can use a sort of a system to select the size, because you see, as a function of their size and their charge, you can they have different velocity. And different trajectory, and then you can really select one size if you want to select one size, and then you deposit on the sample order. So you see the machine is a bit, well, it looks like a bit like a synchrotron actually. So this is the first source we use. The second source, the same idea. Now instead of a magnetron, like a magnet, now you're doing laser ablation. So it means you have your target, the same. If you want to do silver gold, you can use either an alloy target, silver gold, and you ablate with the laser. Or you can use two targets, pure gold, pure silver, and then you can mix the two. This is about how it's done here. You see, you can have the two metals, they are mixed. You just have to adapt the pulse of the two lasers, so you need two lasers, of course. And the same principle, so you have the helium, that is the gas with the pulse. And so we have this ablation chamber. You've produced this plasma of atoms, then they need to cool down and make cluster. And once again, they can go into a mass selector. And here you have a mass spectrometry. So you can even see what you have in your beam. So you can detect which are the cluster you are forming in your beam here. And before deposition, and then of course, if you put the sample order, the substrate, then you stop the mass spectrometry. So once again, you see the laser here, and this is so everything is of course in vacuum. So in principle, you can make any type of cluster, any size. But okay, it's not as simple as this. The advantage, of course, is much better defined than in chemistry, because you're really depositing exactly the cluster you want. You don't go onto the support when you don't have to do an additional treatment to reduce them so they should be almost ready as they land onto your substrate. So as I said, that's what we need actually to really understand the active site and how this cluster works. So EXAFS is there, but you see, it's not enough. So you need, we need this mass spectrometry inside the gas before they are deposited. Then once they are deposited, we need to see how many we have. We use RVS, we can use SEM. Then we go for TM to look at the structure, the detailed structure. Are they bimetallic? Are they core shell, alloy? Then we can use also XPS to see what's the electronic state on the surface. EXAFS gives you the rough idea of the structure. So it's really let's say the foundation. Drift, so infrared spectroscopy is also very, very informative, because now you can really look at what happened on the surface. So if you have like probe molecules, like CO, for instance, you will see which atom will bind to CO, how the thing will evolve with time. So this is very good. And of course, you need the DFT. So DFT is a sort of so you see, this is about all the technique we used. So it's not a very easy way to do, but fortunately, I think it's absolutely. And the good thing is that our systems are pretty well defined. That's why you can really understand what you have. So this is the goal of our work. to unravel the dynamic structure property correlation and identify the active sites. So I will show you 3 examples of new catalysts. Let's say they are not new, but we use this novel method to produce them, and we saw so interesting things. So this one is just a typical gold catalyst, and it's site selected. So we made it with the magnetron, and we selected the site around 3 nanometers. So you see this is a pretty good selection. Why? I mean, of course, the more selected you want, the more time you need, the more money it costs. So okay, you need to have something reasonable. So you see, you can make this. You deposit onto this electrode. This is FTO, fluorine dot tin oxide, and you see the small cluster everywhere. You can control how many you want, if you want high loading or just. And then this is the high resolution aberration corrected stem. So you can really see the structure. You see even the atoms, and can almost see even the shape, the crystalline structure. You see probably some facets. So we made this new electrode with this, and Anupam studied them in a cyclovoltammetry. And I mean, I didn't expect that, but these samples, they are much higher activity than the typical gold nanoparticle. So this is the CV. So you see, you cycle as a function of potential, and these 2 peaks, they are corresponding to the. So maybe I didn't mention this. It's the methanol electrooxidation here. So this is for fuel cells. So these 2 peaks are they correspond to the electrooxidation, and they are. I mean, you can measure the area, and it gives you the activity. And of course, if you continue the oxidation, you make this oxide on the gold. But what is very good here is that everything is reversible. So you can make some oxide, but you don't destroy your catalyst because it's coming back exactly where it was. So it's very stable. And now, if you look at the comparison of the different catalysts, you see these are the ones we find in literature, but gold nanoparticle, and this one is like 10 times more active in terms of mass activity. And even this one is being made with the other machine. It should be less defined and the same. It doesn't have such a good activity. So now the question was, what is the reason for this activity? So we went to DFT group and the best it was. So the idea was to calculate. You see, if we start from the idea that probably, because there are not so many possibilities with gold, probably the surface, the shape of the surface is the very important point. So we try to calculate the CO energy of absorption on a different side. See, this is the corner, these are the edges, and we can see that there is a special site where the CO is absorbed much more strongly here and here, and the same for OH. So from this investigation, we could see that this structure with you see these facets, the edge, these are the very active sites. So if you have the same nanoparticle, gold nano, that doesn't have all this nice structure, it will not be very active. So, and the good thing was this size, because of course, let's say the shape of the cluster is also depending on the size. And for this 3 nanometer, we see a very nice faceted structure with a high density of active sites. So I think this is an interesting point, because at the beginning I was not very optimistic in terms of new novelty, but you see, even with gold, you can see novel things. The second example I wanted to show you is the gold silver. So this is the work of Tinway, and yeah, I think we were interested in the composition-dependent nucleation, because you see, as I said, you need to know where the 2 atoms, when you have a bimetallic, are going. How they are, because you start, of course, with here you see this is a paper I find this is made in colloids, and they try 2 different pre-nucleation species with different geometry, and then they check at the final particle, and you see the 2 distribution are very different. So it gives the impression, of course, that the original spaceship during the nucleation, they're already giving some orientation about how the particle could evolve to which structure, core shell, other alloy, other separated phases. So I think it was very important to understand this parameter. And so what Inoue did, he made a full collection of different silver gold cluster with different composition. So we're keeping more or less the same size and the same coverage. Everything is the same. And you see, for different composition, we use the high resolution microscope, which is, of course, depending. This one is a contrast, which is HFDF. It gives you different contrast according to the elements. So the light elements are darker than the heavy elements. For instance, here the gold is the higher weight element, so it will appear like very bright, and the silver, which is dark, it will appear, which is light, appear a bit darker. So these are the different measurements, and you can see. Okay, it's not so obvious, but you can see in the middle, for instance, here you see like a black spot. And on the contrary, here on this one, you see the core is more bright. And this is the simulation they made in terms of height and shape. And you see clearly that each time it seems that the minority element is in the core of the particle. Here it's gold, here is silver, that is in the core, here it's gold. And this one is really 50-50, is an alloy. So once we had that, we also did this X-ray absorption. So they had to make this very long sample. You see, you need to because we are only on the surface, so we have very few atoms, and we really need to have the X-ray parallel to the surface. We use the fluorescence detector, and even with this, we didn't get very good quality, but still, I think we can feed the data. And you see that you have, for instance, if you look at the Ag distance, you have different distances according to the composition. So a lot of things are changing. It seems that everything is a bit reproducible. It's not. Even the AGU distance is also changing during you have different composition, and every time you have a change, it means something. It means that the location are different. They are not in the center. They are the core. They can be on the surface. So it's a difficult analysis, but each information here can give you some idea where the element is. But as I said, you have to combine. So you need to combine because it's too difficult. So this we stayed, and then we did the XPS. Also, we could see this is so we measure how many pure we have in each one compared to the low phase. And yeah, you see, for instance, that you can go to 40% of pure. So it's in the sample, it's not very well mixed. You know, it's not mixed at all because there is a lot of pure inside the cluster. Here is pretty mixed in the 0.5, but then it's not so well mixed. We also saw some charge transfer, and I think the final idea was the minority element very often in the core of the body. So how to explain that? We try to explain that by the idea of the nucleation. So we made some, we discussed with Riccardo Ferrando in Genoa, and he made this, I mean, we couldn't find an explanation actually. So we asked him what he was thinking, what sort of idea how we could explain it. And I think he had this idea of looking at the very, very early stage of the nucleation, like the very small cluster. When you start to make the cluster, you have a stage when you have very small cluster, and he calculated the mixing energy, and you see that it's very clear that the mixed, let's say the small cluster with two elements, they are much more stable. So this, it seems that is a very good explanation why you are forming always this bimetallic structure at the beginning of the cluster. I think that is interesting because we could confirm with the mass spectrometry. You see here, this is inside. We can see all the different clusters we have in the beam. So we have all the small clusters that are, and we see that the ones that are mixed, they are more abundant. So you see the 3 and 4 atoms, they are overrepresented in this area. The other one, they have different composition, but the very small, they have a very typical composition here. And from this, we started to, let's say, propose a sort of a nucleation model. And we have like 4 steps when we first here in the first stage in 2 atoms are generated by the laser ablation, so they are separated. Then we start to form into very small bimetallic cluster, the very small 4 atoms we mentioned before. And of course, because the bimetallic I favor is depleting the minority element from the gas phase. So you end up by accumulating all the minority element in the core, and then when you don't have any minority element left, and you finish with the majority element. So that's why you see, that's what you see in the core. All the minority element is in the core, and then you end up with the majority element. So here, for instance, Ag1, the silver is in the core and gold is outside. And here is an example of a perfect alloy. And then you do the contrary at a high content. And the gold is in the core and the silver is outside. Yeah, so this is really the idea and I think it's probably correct because we find, I will show you, we find the same pattern with a different system. But of course, this is probably connected to the cluster fabrication. I'm not saying that it will necessarily be the same mechanism chemically or with different preparation method. So this is the last part I wanted to show you we made platinum nickel for the methanol dehydrogenation. So then we made 3 different compositions, and you see the same principle as silver gold. You see here that the platinum, which is the heavier element, is in the core, and here the core is a bit darkened because the nickel is probably in the core, and then you have an alloy. So I think it's pretty convincing when you see the relation. So the same idea as the silver gold, you have PT and nickel, and you see the mixed cluster have a lower energy than the pure one. So you have the same mechanism when you concentrate the minority element in the core. They make 2 nanometer cluster. So I think, yeah, we mainly did XPS on the system, and I think it was already very interesting. And you see some nickel oxide, hydroxide in the nickel rich, and pure platinum and PT rich, they have a lot of PT oxide. Yeah. So you see clearly that when you increase the content of nickel, you have less oxidation here for the this is the platinum, and here when you put more nickel, of course you have more oxidation. And so this is what Tinway did. He also made the machine actually. So this is the temperature program desorption. So this is something that is, of course, everything is happening at very low pressure, 10 to the minus 10 millibar. So you have your system here with the cluster deposited on the surface, you have a gas doser, so you want to desorption, so you want to absorb first methanol at low temperature, and then you will heat to see what comes out. I mean, to see what is being transformed. So this is the methanol decomposition, and you have a quadruple mass analyzer, so you will pick up with time, with temperature, what appear in a gas. And the reaction, so we did also deuterium, because of course it's much easy to control, and then the reaction is there. And this is what you get for the different composition. So you see here, you need to go to very high temperature to dissolve CO from platinum, which is equivalent to being poison. So we know that CO is poisoning platinum. So this is one of the big issues. But you see also that if you increase nickel content, this poisoning is going down. So for instance, here you can dissolve at lower temperature, then it doesn't move that much. If you look at D2, the absorption, you can see also that you're decreasing the absorption here, and then you have this minimum value here. So in terms of activity, it's very clear that the 0.3 is much better because we are reducing so much the poisoning. And we saw an activity of 60% more than, sorry about this, 60% more of the pure platinum. So this composition is special. And once again, we wanted to try to understand why this composition could be special. And we also did some DFT simulation. So the idea was to calculate once again what was the absorption of the absorption energy for the CO on the different atoms of a typical PT nickel system. And because we know also that at this composition, platinum should be on the surface. There are several proofs, and we saw the electron microscopy, we saw the desorption, the XPS. It's pretty clear that platinum is mostly on the surface. So we come up with this model of a PT skin. So the cluster, let's say the surface is really platinum, but just underneath you have a lot of nickel. And this nickel, so this is the idea. And if you make the calculation, you can see very well that, so this is the CO binding energy as a function of the decenter of the band of platinum. So you know, when you're making an alloy, you're changing the D-band position. And if you change the D-band position, it is modifying the state of the CO, and then you weaken the antibonding states will be stronger, and you weaken the CO interaction. So I think this is something we are looking for to diminish the CO binding energy. And indeed, if you look at these sites here, when you have this PT nickel system, you really have lower CO binding energy, and you have a D-band center that is shifted here from 2.5 here in a typical, so maybe it's not clear, but this is only PT, and it's PT with nickel, so it's a bit complex. But you see, this is the typical, even the PT, pure PT is there, it's a bit there. So you see with PT nickel skin, you really diminish the D-band center, and you diminish the CO absorption energy. So by doing that, you really increase the activity. So in conclusion, we have shown that the CBD cluster have a high density of active sites. So this is much easier to study them. That's why we are focusing on this compared to the typical cluster or nanoparticle made chemically. We can confirm indeed that the catalytic activity is tuned by the size, because the size is controlling also the type of atoms you have on the surface, like corner, edges. So this is very important. And the composition also, because you have, as I said, you have multiple arrangements. You can have, you see, like a typical alloy, but in fact, most of the time it's not an alloy. can be very sophisticated combination, like PT skin with nickel below. It can be a region also on the cluster with different regions. And so that's what we think, we hope the design of novel catalysts with CVDs will be promising, and that's what we're doing with the CACHI network. And then I want to thank Anupam. So Anupam and Tinway, they were the student of the CatSense project. So they were very busy with all this bimetallic cluster, optical deposition. And these are all the people that collaborated. So a lot of people from DFT, Tibor, Kari from Budapest, from Finland, Noval, Troy is in China, is doing electron microscopy. This is Francesco, is the head of the LISA beamline. Olga, she's working at the Swiss synchrotron. Piero is from our group, postdoc from our group, and yeah, other people, Michel Palmer, I don't know if you know, probably know him, and Ewald and Peter. And well, I think that's it for me, and I will thank you. I want to thank you for your attention. And of course, if you have a question, we can discuss.
Thank you very much, Didier, for this nice presentation. Now, well, the seminar, so there are some open questions. Podemos pasar a la sección de preguntas, chicos, ya sea que lo quieren escribir en el chat, si tienen alguna pregunta, o si no, pues directamente a Didier, abrimos los micrófonos para preguntarle directamente a Didier. So you can write down your question in the chat, or you want to ask directly to Didier, please feel free. Don't worry, I can.
Yeah, you can tell me, because I'm not sure I can see the chat actually.
Yeah, sure, no worry. Yeah. If there are some questions in the chat, I will just let you know. Okay. So Didier, I just have a kind of a more technical, well, not question, but I would like to know your opinion. Did you know that here there were some rumors about here in Mexico to build and start a synchrotron in the Mexican territory? So based on your experience on, what could be or would be the budgetary information about, starting up with this kind of, venture, and what will be the cost of maintenance yearly? I mean, I know that, for instance, you have information on DSRF, and that's, I think, the biggest one in the world. But let's say one small one little one.
Well, I don't know if I can give you very precise figure, but I don't know if you know that there is a synchrotron in Jordania.
Mm-hmm.
So it's just close to the Dead Sea. Well, it's on the other. It's very close to the Israeli border. But there is a synchrotron there. I mean, obviously they don't have a lot of money, so this has been sort of offered by Germany. I think they took all the pieces of a synchrotron they dismounted in Germany, and they rebuilt a full synchrotron in Jordania. Even discussed with one of the scientists there. Well, at the time he was afraid to be caught in a bombing and maybe lose his life. But yeah, I think for Mexico it's probably okay. I mean, then as you said, you have very different types of synchrotron. Huh? You have very basic one. You have even all these devices. It's not only the synchrotron. Then you have to buy all the equipment for each beamline. It costs a lot of money. If you want to have a very good detector, it costs millions of euro, dollars. It's so the building the synchrotron is something, maintaining is something, but also each beamline is a lot of equipment. It's a lot of stuff. Yeah, I mean, at one stage it was very fashionable to have a synchrotron. Probably every city wanted to have a synchrotron, but now they're starting to see. Actually, they want to even to charge the beam time to the universities now.
Okay.
So I don't know. People are maybe changing their mind, but what do you think? I mean, you think a synchrotron would be useful for Mexico?
Well, I'm just thinking, because there are many factors, as you mentioned. Also, you need to train scientists, right, to run the synchrotron as well, I don't know. I mean, it's highly skilled people also working over there.
Yes, you have
And
to.
my biggest worry is that, or my biggest concern is related to the maintenance, because I guess the maintenance is also
Yeah, but you're also
um,
maintaining the planes in Mexican Airlines. Huh? I mean, they're not falling down. I mean, so
no.
I
But
guess if you know what you have to do, probably no. I think it's possible. It's just, is it really necessary to have? I mean, I don't know where you could go. I mean, okay. Mario came to the SRF. Okay, it's not very easy, and of course, Mexico could also take a share in the SRF. For instance, India has a share.
I think that would
Israel.
be a better idea, no? Instead of trying to build your own
Yeah,
stuff.
because
I
then you
guess.
can collaborate with the ESRF. You can be reimbursed when you travel there. You can start to build new connection, and then yeah, because as I said, it's very fashionable to have a synchrotron. It's like a nice equipment, but is it? Yeah.
Yeah, is it feasible to maintain it? Well, we have a question from colleague Juan Jose Nava, and he says, based on your experience, is there a necessity to use a different theoretical approach beyond DFT to calculate properties for those clusters? Didier?
Well, we mainly work with DFT. My concern is, I don't know. I mean, I'm not a specialist of DFT. What I want is that the result fit the experimental data. I mean, this is we've been working with the Kong for a long time, so it's pretty long because, as I said, in general, when I start collaborating with someone, when I tell him, okay, I think the system is probably something like this, and then they say, no, it's not possible, it's impossible. I say, okay. And then after a while, yes, they say, oh yeah, you're right, it's possible. So of course, when you start doing calculation, you start with a model that you have to imagine yourself. So most of the time, what you see in science is something that nobody would have predicted. So how can you see, how can you go in the right direction? So this is a bit the problem with the simulation. I think we mostly use DFT, yes. But I think it's not really the technique. The problem is that how would you, let's say, assess your result? How would you validate your result? Because the same for DNA cluster, we did some work. I mean, I saw some result of the DNA cluster. I mean, it was not at all what I thought. Yeah, not at all. So it's difficult to start with the.
Yeah, especially at the atomic scale, I think. No? So we have a question from Mario. He says, or he asks, of the different techniques you presented, Didier, in the cluster study or to study clusters, can GSACs be used to determine the internal organization of clusters?
GSACs, well, of course, he will tell you the size, the shape. There's something we wanted to do. We did some GSACs on this gold-silver cluster, but I think it never been published. And at the end of the day, we were not very impressed by the result. It was not so clear because GSACs is very important that your system is extremely homogeneous. So you see all these SACs, all these diffraction things they need order. So as soon as you have an order system, it's perfect. But if your system is not order, so if you, for instance, you need to have the right size. I mean, the GSAC is no longer scattering, so you need big structure, but they need to be identical. If you have a collection of sizes, then you're losing all your signal, So then it's very difficult to say something. But yes, I think if you have very defined cluster, the same size, everything, then probably yes, you could see. But still, TM is better for the organization.
But okay, I guess that the requirements for TM also sample preparation be approached.
Yeah, but they have to be very homogeneous. I mean, as soon as you lose the, as soon as it's very dispersed in terms of style, you see you're blurring everything. You have no signal.
Yeah. Thank you, Didier. I don't know if there might be another question, alguna otra pregunta para Didier, para nuestro invitado el día de hoy. Lo pueden escribir en el chat o si prefieren preguntárselo directamente, adelante.
So, are there many people working with the EXAFS in Mexico? Do you know?
Well,
different groups?
Pretty hard to say, I say, because we don't have the facilities over here. So we need to go, for instance, Stanford, no, is the closest one we have. And also we have the one in Campinas in Brazil, you know. But again, you know, I know that there are people working on this, and there is this group, you know, pushing for to get the synchrotron over here. But I don't know.
I mean, Mexico is still a big country. I mean,
yeah, sure. I mean, there is also.
I don't know. I mean, look at Vietnam. They are decided to invest a lot of science, and it depends on the policy, of course. If you want to develop more science, then yeah, why not? You could build.
And you know, UNAM, you know, researchers at UNAM also working heavily on clusters like you guys do. You know, I mean, there is like plenty of opportunities, let's say, to use those facilities. It will be really nice, but I think like in terms of budget,
maybe I don't know. I don't want to be in a Mexican policy, but why don't you try to have some slots on ESRF or
that would be better, you know. But that means that the willingness to reach ESRF and start doing this negotiation, because also it's not that cheap, you know. I mean, it's cheaper, but not.
Think, you know? Science is not cheap. Huh?
Yeah. Science is not cheap. Yes, you said it.
But
you nailed it.
We should bring some money back.
Yeah, that's for sure. It would be kind of an application as well,
you
know, retribution to the society as well.
No, it's a development of society, so I think it's worth it, huh?
Yeah. I think it too, but decision-making politics or policies are.
It's strange that there are not. There must be a group somewhere that is a bit more, let's say, used to with synchrotron technique. I'm sure, no, in Mexico City.
I'm pretty sure that they are, you know, working on those topics. But again, you know, outside Mexico, you know, I mean, you know, we don't have the facilities, or even in collaboration with some European partners, because in Europe you have in France, in Germany, in Spain you also have one, you know, the Alba, in Barcelona, I guess.
Alba.
You have, well, the ESRF, which is the biggest one, and then
UK. Soleil in Paris.
UK also have.
UK, Diamond. They have.
Diamond, Germany.
Even in Poland, they made a new synchrotron. But it's interesting actually because they made it very cheap. So they have. I think they want to be efficient in Poland, so they built a new synchrotron, but it's I don't know, on the cheap side, let's say, but probably interesting.
But if it works for them, then it's fine, you know. I mean, why not?
Yeah. No, maybe you could contact. It has to be reasonable.
Yeah, sure. We cannot go fancy, you know. That would be just like to start with, you know. Okay, I think that there are no more questions from the public, from the audience.
Thank you very much.
Thank you very much for your talk. Thank you very much for accepting the invitation, and we hope
thank you very much.
Keep this long-standing collaboration we have.
Yeah, indeed. This is,
okay.
We can continue, of course.
Thank you very much. Have a nice weekend over there. Enjoy the hot weather in Europe now. So,
thank you very much.
Para todos. Have a nice weekend.
Disfruten el fin
de semana.
Thank you. Bye-bye.
Nos vemos hasta el próximo seminario. See you.
Bye-bye.